Welcome students. The topic that we'll be discussing today is the magnetic moment of a nucleus. So all of you must have come across the term magnetic moment. So what is the magnetic moment? It is a parameter which you can say it represents the strength of a magnetic dipole. So what about the magnetic moment of a nucleus? Does a nucleus have a magnetic field associated with it? If so, where from it arises? But it has been experimentally found that almost all nuclei they have a certain magnetic moment associated with it. So the nuclear magnetic moment can be defined as the resultant magnetic moment possessed by a nucleus. So we'll look into it where from this magnetic moment for a nucleus it arises. So where it comes from is basically from the protons and the neutrons which comprises the nucleus. The nucleus is composed of the protons and the neutrons. These are together called the nucleons. So it has been found that these nucleons, that is the protons and the neutrons, they possesses intrinsic magnetic moments. So when they come together to form the nucleus, these intrinsic magnetic moments they add together to give rise to the total observed magnetic moment of a nucleus. So the nuclear magnetic moment is nothing but the sum total of the magnetic moment of its constituent protons and neutrons. So we can represent diagrammatically something like this. The nucleus is this and it possesses a finite magnetic moment which is represented by the symbol mu. So we need to find out an expression for the magnetic moment of a nucleus. So for that, we have to fall back to the fact that any current loop has an associated magnetic moment. So for a nucleus, where from the magnetic moment arises, it's because the nucleons inside the nucleus, that is the protons and the neutrons. The protons are obviously charged particles, and even the neutrons, although they are neutral as such, they have a charge distribution within it because of the quarks which comprises of the protons and the neutrons, which are made up of the quarks. So these quarks they have fractional charges. So inside the proton and the neutron they have charge distributions, and overall if we look into it, the proton has a unit positive charge, whereas the neutron as such is neutral, but it has a finite distribution of charge. So these protons and the neutrons they have associated angular momentum. When we talked about the nuclear spin, we discussed about it. Apart from the spinning motion, apart from the spin angular momentum, which is associated with the protons and the neutrons, they also have an orbital motion about the center of mass of the nucleon system. As such, they possesses both spin motion and orbital motion. So any charged particle in a circular kind of a motion is constitutes a current loop. And from classical electrodynamics, we know that any current loop is associated with a magnetic moment. Current loop, it will be associated with a magnetic field of its own, and this, because of this magnetic field, it has an associated magnetic moment. So if I have a current loop of an area A, suppose radius is R, it has area A, and the current flowing through the loop is I, then the magnetic moment associated with this current loop is given by mu is equal to IA. This is a vector quantity. So this is the expression for the magnetic moment associated with a current loop. So this can be written as mu is equal to Q by T. So if the charge going around in the loop, charged particle going around in the loop has a charge q, and it takes a time t to cover the whole circular loop, then q by t gives you the current. So if you are standing at any point of this loop and looking at the charge passing by. So after every time t, that is the time period, you will see the charge moving past you. That means the rate of flow of charge for this current loop, that is the current, is q by t. And if r is the radius, pi r square will be the area of the current loop. So the magnetic moment is given by Ia, that is q by t pi r square. Now, if v is the velocity of the charged particle going round the loop, then the path length of this current loop is given by twice pi r. That is the circumference of this loop. So the time period will be twice pi r by v. So this expression can be written as qv by twice pi r and pi r square. Hence, we can simplify it to qvr by 2 multiplying and dividing by the mass m. If m is the mass of the particle, it becomes qmvr by 2m. Now this mvr represents nothing but the angular momentum L of the particle. If a particle of mass m moves around a circular loop of radius r with a velocity v, the magnetic moment associated with this particle is mvr. So the orbital angular momentum associated with this particle is mvr. So the expression for magnetic moment can be written as mu is equal to q by twice ml. So this is a very important relation between the magnetic moment and the angular momentum of an orbiting charged particle. Any charged particle of mass m and charge q moving round a circular path has an angular momentum L, so the magnetic moment is given by this expression. Now, in a nucleus, the nucleons have orbital angular momentum and spin angular momentum. This we have already discussed. The protons and the neutrons, they have orbital angular momentum and spin angular momentum. So as we have seen here, as we have seen here, any angular momentum associated with a particle with finite charge and mass will have an associated magnetic moment. So, in the nucleus, because of the orbital angular momentum and spin angular momentum of the nucleons, that is the protons and the neutrons, finite contribution will be there to the magnetic moment. Or if we consider a single nucleon, it will possess finite orbital angular momentum and spin angular momentum and associated magnetic moments due to the orbital motion and the spin motion. So when we have a nucleus comprising of nucleons, in total the nucleus will possess a certain magnetic moment. Now the magnetic moment due to the orbital motion of neutrons is zero because overall the neutron is neutral. So Q is equal to 0, that is the charge is equal to 0, even though it has a finite orbital angular momentum L. The neutrons, because of the fact that their overall charge is 0, it's neutral, it contributes nothing to the magnetic moment because of its orbital motion. However, for the protons, it will contribute because of its orbital motion. Also, there will be finite contribution to the magnetic moment because of its spin of both the protons and the neutrons. Although the neutron overall is neutral, as I told you, it has finite contribution to the magnetic moment because of its spin and hence the spin angular momentum. Why? Because there is a non-uniform distribution of charge inside the neutron. So when the neutron spins round, it constitutes tiny current loops because of its non-uniform distribution of charge. However, because of its orbital motion being overall neutral, it will contribute 0. Now, these contributions because of the spin motion and orbital motion. These contributions to the magnetic moment because of the spin motion and orbital motion of the individual nucleons in the nucleus adds up to give the resultant magnetic moment of the nucleus. So experimentally measured values of magnetic moments for the protons and neutrons are: proton is 2.7927 nu n. So nu n is called the nuclear magneton. This is a unit of measurement of nuclear magnetic moment. And the neutron, its magnetic moment is aligned opposite to that of the proton, and it's comparatively much lesser. Here, for the protons, its contribution because of both the orbital motion and the spin motion. For the neutrons, it's only because of the spin motion. So, expectedly, its magnetic moment is lesser. So, nu n is EH crossed by twice MP is called the nuclear magneton. It has a value of 5.0571 into 10 to the power minus 27 joules per Tesla. And MP here is the mass of the protons or the neutrons, and or we can call it the mass of the nucleon as such. So for a nucleon, if we consider a single nucleon, the expression for magnetic moment due to the spin and orbital motion together can be written as mu s, representing the contribution to the magnetic moment due to the spin, is g as e by 2m into the spin angular momentum. E is the mass, the charge of a nucleon, m is the mass of a nucleon. So Gs is a Gl and Gs here are dimensionless correction factors, also called the spin G factor or the orbital G factor, and are different for protons and neutrons. So as we have discussed, there is no contribution to magnetic moment from the orbital motion of neutrons. So for the neutrons, Gl will be equal to 0. However, Gl is equal to 1 for the protons. And sorry for this. And Gl is equal to 0 for the neutrons. There is a typing error here. Gl is equal to 1 for the protons and Gl is equal to 0 for the neutrons. Gs, on the other hand, is 5.586 for the protons and Gs is equal to minus 3.826 for the neutrons. These are correction factors. So the total magnetic moment due to a nucleon can be written as the sum of the contribution to the magnetic moment due to the spin motion plus the contribution due to the orbital motion. So this together can be written as E by 2m GSS plus GLL. So adding up these two terms, contribution due to the spin and orbital motion. And m, again I am telling you, it's the mass of a nucleon. That is the mass of a proton and a neutron. So for a nucleus as a whole, which has a mass number A, that is total number of nucleons is A, the nuclear magnetic dipole moment can be written as E by twice m summation over k is equal to 1 to A. We have to sum over the contributions to the magnetic moment due to all the nucleons inside the nucleus. So this is the idea of summing over from 1 to A. So for the first nucleon, because of the spin, because of the orbital motion, for the second nucleon, because of the spin, because of the orbital motion, everything will add up together to give us the total magnetic moment of the nucleus as a whole. So this can be written as E by twice m summation k is equal to 1 to A Sk plus Lk. So this Gs and Gl, we are clubbing it together as a constant G. So for spin motion, G will be Gs. For orbital motion, G will be Gl. So we are clubbing it together into a single constant. We call it G. Now, from our earlier discussions, summation over the spin angular momentum and orbital angular momentum for all the nucleons, it gives me the total angular momentum of the nucleus as a whole. This total angular momentum of the nucleus, I, is called the nuclear spin. So I, this term here, is equal to the nuclear spin. So the magnetic moment can be written in terms of the nuclear spin, that is the total angular momentum of the nucleus. So we can write mu as g e by twice m I, where I is the nuclear spin. So multiplying and dividing by h cross, I by h cross. So this can be written as mu is equal to g mu n I by h cross, where mu n is equal to eh cross by 2m is equal to 5.04 into 10 to the power minus 27 joule per Tesla is the nuclear magneton, which we have discussed earlier. So what is G? G is also called, it's a dimensionless ratio, and it is called the gyromagnetic ratio. It is a ratio of the magnetic dipole moment or nuclear magnetic dipole moment of a nucleus expressed in units of nuclear magneton to the nuclear spin in units of h cross. Again, I am telling you, G is a dimensionless ratio called the gyromagnetic ratio. It is the ratio of the nuclear magnetic moment expressed in units of the nuclear magneton to the nuclear spin expressed in units of h cross. So this expression gives us the nuclear magnetic moment for a nucleus. So if we can measure the nuclear spin, we can immediately get a measurement for the nuclear magnetic moment for that particular nucleus. So this nuclear spin, as we discussed in the earlier lecture, can be measured experimentally. So when we discuss the shell model of a nucleus or the single particle model of a nucleus, we'll be talking about measuring or determining the nuclear spin of different nuclei. So that is all for the nuclear spin. Thank you.